The topic of our second project is vulnerability map for Ogallala Aquifer for a certain contaminant. My name is Zaki Ahmed Choudhury, and our other two group members are Kushum Kesi and Raksha Shrestha. So Ogallala Aquifer is one of the largest aquifer of the United States, and it lies under northwest Texas part of it. And most of the water of this aquifer is used for irrigation purpose. It has a shallow water table, and so it is at a high risk of over extraction. The contaminant that mostly we find in this aquifer is fluoride and arsenic. We do not consider arsenic as a contaminant that we want to model because arsenic is not really introduced from the surface, and so the only candidate that remains is the fluoride. Also, we have a vast amount of data for the fluoride contaminant. Sources of fluoride in the underground aquifer is in the underground aquifer, the fluoride comes from two sources. One is the municipal water that we use and then discard on the surface, and another source is the fluoride bearing rocks that we find underground, and whenever water passes through the rocks, that dissolves some of the fluorides. Fluoride has some health benefits, especially at low concentration, but at high concentration, it may cause dental fluorosis and skeletal weakness, and it also may hinder brain development. The cutoff for fluoride concentration for our model, we took it as 1.5 milligram per liter.
So for data compilation, we took PRISM data. In that, we consider precipitation, elevation, and temperature. From Texas Water Development Board, we took major aquifer water quality data because Ogallala is considered a major aquifer. So next, we took well main data, and from sorghum data, we also took sorghum data for soil parameters. And for data filtering, we took for PRISM data, we took 30 years normal data. For TWDB data, we took the data after 2080 because we wanted to obtain sufficient spatial coverage across the aquifer. So for spatial zone, we consider Ogallala Aquifer, and for parameter, we took fluoride concentration. For this, we averaged the fluoride concentration for a unique well. After that, for sorghum data, we created map from both Python and QGIS. So next, so these are our variables that we considered in the beginning. Here, Tmean, Tmax, and Tmean are temperature, minimum, maximum, and mean. So Ksat are the conductivity of soil in low, high. So AWC is amount of water content, and pi is PI is plasticity index.
Our other next step after getting the data set is variable selection. Our Y variable is the fluoride concentration exceedance indicator, while our X variable would be considered the independent of each other. So for that, we check the coordinality between the variables itself. For that, we use the Kendall density function, which calculates the rank correlation coefficient. The values indicating 0 means there is no correlation. And for the feature importance check, we use the decision tree and random forest. Both the decision tree and random forest use a tree-based selection method. So this is the output from random forest and cart method used by the tree method. But the random for the hyper parameter for random forest would be the number of nodes to be considered in a decision tree. Using the result from this, we can see that our parameters like well depth, rainfall, elevation, available water content, the temperature, clay total are the ones that should be given importance. So depending upon this one and the correlation test, we determine the first set of variables for our first model, which is well depth, rainfall, elevation, available moisture content, temperature, plasticity index, pH, and clay total. So for the logistic regression method, our X variables are classified into binary zeros and one, and the data has been split into training data and testing data. The model is fit for the training data, and the same model is fit for the testing data set. So the hyperparameter included in the logistic regression is C equals 10 to the power 9, where C is the regularization strength. If we take the higher value, it represents that the model is fit more closely to the training data set. In the Python from scikit-learn, we can use the logistic regression. So after the logistic regression for all the variables from the model 1, we got the precision of 0.78 and recall of 0.99, which indicates that our model is better in predicting the one values, that is higher concentration than the lower concentration. The area under the curve of the ROC curve indicated 0.7, which is higher than the random given by the random classifier. The same model was fit for the testing data set, which indicated that the recall value indicated that it is good on predicting the higher concentrations of fluoride than the lower concentration, and the area under the curve is still greater than the random classifier. The next method used is the naive-Bayes classification method. It's a probabilistic method. So the main assumptions for the naive-Bayes classification is that the y variables are conditionally independent given the input variables, which is not always true. But the other naive assumption that it makes is that the features are independent of each other given the class levels. That makes it a naive-Bayes classification. So there is a in the Python, there's a library Gaussian NB which uses the package scikit-learn naive-Bayes. So using this, we can do the naive-Bayes classification, and from the same input variables on the naive-Bayes classification, we fit the model for the training data set, and the precision obtained from that was 0.8 and the recall was 0.88, which still indicated that our model is better fit for determining the higher concentration, and also the area under the curve is better than the random classifier. So the same model was fit for the testing data set as well, and the testing data set indicated that the precision and recall is better for the naive-Bayes, which was only better for like determining the higher concentration in the logistic regression, and the area under the curve is also greater than 0.5.
We did the logistic regression model part for the fluoride modeling in Ogallala Formation. We collected data from 947 wells, and the parameters we selected were well depth, elevation, rainfall, minimum temperature, soil clay content, average water content of soil, soil plasticity, and soil pH. Elevation was just used as a surrogate uh, for the general topographical slope because of a lack of data for this source. We use elevation. We use rainfall because rainfall causes the surface water that is contaminated with fluoride to reach to the aquifer, and we use the minimum temperature because temperature is related to the of underground underground fluoride bearing rocks, and soil clay content is related to the water retention property of soil. Average water content also uh, is useful to supply similar information, but to a different degree. And also soil plasticity was used. A high level of pH actually accelerates the dissolution of the fluoride bearing rocks underground. As I said that we used the WHO specified level of 1.5 ppm of acceptable limit of fluoride. So we choose this as an exceedance limit. Whenever our limit exceeds the 1.5 ppm level, it specifies a 1 in the model. We divided our dataset into 70% training and 30% test data. After the modeling, we found that the accuracy was almost 0.79, precision was 0.78, and the recall was 0.976. And here is the ROC curve. We can see that it is much better than a random uh, coin flipping.
After running model by taking all these parameters, we are trying to uh, run the models by taking fewer parameters, because if the model works with fewer, gives similar outcome with fewer parameters, why do we need to take this much parameters? So for that, we again ran a correlation among the parameters by doing feature selection among them. Here we can see that in T-mean and elevation are highly correlated. So we are trying to exclude one of them. For that we use feature importance. From feature importance, we can see that the elevation is more important than temperature. So that way we include elevation. We do that. Similarly, we take AWC in place of clear total. And after that, these are the parameters which we took for third model. So in this model also, we can see that the model capacity to predict one is uh, higher than for 0. So it is giving the similar kind of outcome. Here recall is 0.995, while the accuracy and precision are lower. So area under the curve is, we can see that it's 0.69. It is slightly better than a random classifier. So for testing data also, we can see that the model capacity to predict high concentration is better. And similarly for naive Bayes also, we can see that that the model capacity to predict high concentration is better. Here model capacity to for predicting one is 454. So area under the curve is 0.72. That means that the model is better than naive Bayes model is better than logistic model. In testing data also, we have found a similar outcome. So next is KNN, K nearest neighbor. Now K nearest neighbor is it is memorization learning algorithm, which is also known as lazy learners. It is used for continuous variable. Here assumption is that the similar items closer to each other, it considers similar items that are closer to each other than these similar items. So hyperparameters that we include are the value of k. The value of k is number of neighbors to be considered. So weight is the distance between the distance between two points. For that, we took harvest distance. In the in this For this, we use K-neighbor regressor library, which we get from sklearn neighbors package. For so we fitted the models for the training and testing. And for testing, we can see that the predicting capability of probability predicting capability of linear logistic regression is better than naive Bayes, because the line where observed is equals to predicted. The values are highly concentrated around here for logistic regression, while the predicted values are distributed in naive Bayes. So we can say that the logistic gave better prediction than naive Bayes. Next is we created for for KNN prediction using the maze of latitude and longitude by using both models. We created the coordinates by taking maximum latitude and minimum latitude, and maximum longitude and minimum longitude, and we gave the spacing of 0.1 decimal. By this way, we created a grid.
For integrating our models, we compared the independent model performance with the K and fit model performance, and in the independent model performance, the knife-based classifier seems to have better accuracy and precision, but for the K and fit models, the logistic regression model seems to have better alignment with the x equals to y line. So considering both of this error to be independent, we decided to give the equal weight for both K and values, and then we plot a vulnerability map for latitude, longitude of the graded data set and the new Y from the integration. So our conclusion includes that the southernmost portion of the Ogallala Aquifer is more susceptible to the fluoride contamination, and our logistic regression model gave the better model fit while modeling with the same data sets than the knife-based classifiers. So these are our references for the data's literature review. Thank you.